Hey there everybody, this is Mr. Marek, and this is our fourth or fifth or something like that video on thermodynamics, where we actually get to a statement of an actual physical law about thermodynamics. So this one's kind of important, and it's probably going to end up kind of lengthy, but don't think that you necessarily need to write everything down. I'm going to try to go slow and make sure that we kind of review as we go so we can make connections to what we've already learned. So here's our goal for this lesson. We want to be able to explain and quantify the operation of a heat engine, meaning that we want to be able to figure out how much heat is needed to make a particular sample of gas do a given amount of work. That's our basic goal at the end of all of this. So, real quick review. Remember that a gas, the particles that make it up, have kinetic energy because they're constantly in random motion. So a picture like this should be kind of familiar by now. A picture like this should also be familiar. So the question today is, what happens when we take something that's got a high temperature and we touch it to something that's got a low temperature? Now you probably know the macroscopic answer, like what happens as far as temperature goes. But what we need to be able to do is explain this on the molecular level. So here's our hot and cold objects which are in contact with each other. Now I don't feel like you necessarily need to copy all these pictures that I'm going to draw, but do write down some key things that are going to make you understand. What's going to happen? Well, first of all, let's assume that these walls aren't really there, meaning that they don't inhibit the transfer of energy between these particles. What's going to happen is that these particles over here are going to collide and transfer energy with these particles over here. Now the particles within each sample are constantly colliding with each other, but remember, on average the velocity doesn't change. But when they collide with something that's outside of the sample, then the average velocity is going to change. So basically what we've got is we've got two things that are colliding with each other elastically. Remember, elastic means that energy is conserved. So the net result, if you remember doing things like this with momentum carts and stuff like that, is that the thing going fast is going to slow down, and the thing that was going slow is going to speed up. And so the before picture we got one fast, one slow. The after picture, we've got two mediums. So the net effect, if you look carefully, like right around this area, is that some of the energy from the sample on the left, the hot sample, is transferred to the sample on the right, the cold sample. That's kinetic energy, because it's energy due to a collision. And this energy transfer we refer to as heat. So when we say heat is transferred from one thing to another, that's all that we're talking about. Energy is transferred from one set of particles to the other via collisions. And so this process is going to continue. For instance, between these particles right here. And what we end up doing, what we say is that heat is being transferred from one object to another. Now this process is continually happening back and forth until the average kinetic energy, remember that's another way of saying temperature, is the same between both samples. Now that doesn't mean that all the collisions have stopped. The particles in the sample on the left are still colliding with the particles in the sample on the right. However, the net energy change is zero. So for instance, those two guys are going to collide with each other, which is going to cause energy to go to the left. I should say to the right, actually. No, never mind, I was right. Transfers to the left. Goes from high energy to low energy. This collision right here is going to cause energy to go from left to right. So the average on both sides is going to be the same. We're going to have some energy transferred from left to right, but we're going to have some energy transferred from right to left, and those two are eventually going to even out, so that the net energy flow is zero. So basically the same thing kind of happens that we talked about earlier. The average will be the same for all the particles once they're given time to reach this state where the net flow between them is zero. This state is referred to as thermal equilibrium. So those two objects have the same temperature, and we say that they are in thermal equilibrium. So to kind of recap that process real quick, let's take a big picture view. Suppose we have two things which are at different temperatures, one 700 Kelvin, the other 300 Kelvin, and then we touch them together so that they can transfer heat. And I'm not going to show them touching together because what I want to do is show the heat transfer. So that big yellow arrow indicates that a bunch of kinetic energy is being transferred from the particles in sample A to the particles in sample B. So let's suppose that this is at t equals 1 second. At t equals 2 seconds, they're going to have different temperatures. Because heat's leaving the sample A, it's going to get cooler. And because heat is entering sample B, the particles in sample B are going faster, it's going to get warmer. So just as an example, I've got A cooling down to 500 Kelvin and B warming up to 350 Kelvin. Now notice that those temperature changes aren't necessarily the same because sample A and B could be different. They could be different sizes, they could be made out of different things. So I don't want you to think that those temperatures are necessarily going to meet quote-unquote in the middle. They're most likely not. To kind of continue the picture, we still have a substantial amount of energy going from A to B, but not as much as before because we've got some small amount of energy being transferred from B to A. So the net effect is that the amount of heat is less in the second heat transferred is less in the second second than it was in the first. At 3 seconds, those two rates of heat transfer might be equal. When that happens, the temperatures will both be the same. So maybe their final temperature is 400 Kelvin. That's when they're in thermal equilibrium. So over here on the right, if we were to draw a LOL chart of the two objects as a system, both would have some starting internal energy to start with. So UA, internal energy of A, UB, the internal energy of B. And then when they reach thermal equilibrium, the internal energy of A will have gone down, the internal energy of B will have gone up. Again, those energies aren't necessarily going to be the same. The temperatures will be the same, but not necessarily the amount of energy. If we were to create a graph of temperature versus time, like starting at 0 seconds and then 1, 2, 3 seconds, object A slowly loses temperature and object B slowly increases in temperature. The rate is going to be largest at the beginning when they have the biggest temperature difference, and they'll eventually converge to some temperature which is the same. In this case, it's the 400 Kelvin. So they're going to start off changing temperatures rapidly, and then that temperature rate of change will gradually slow down. So again, these two things are going to end up with the same temperature, not necessarily the same amount of energy. If we kind of put some numbers into this example, if object A started out with 700 joules of energy and ended with 500 joules of energy, object B started out with 200 joules of energy, then it would have to end with 400 joules of energy. So a net transfer of 200 joules occurred from A to B. That's typically always going to happen. The warmer thing will lose energy, the cooler thing will gain energy. So let's recap. Our definition of heat is the net kinetic energy that's transferred from one object to another. Now, there's different ways to transfer the energy. We're going to talk about those later on. The symbol that we use to indicate heat is a Q. And if you've taken AP chemistry and you remember enthalpy as delta H, for example, don't get that confused with heat. It's got a different meaning. Heat is the energy transferred. So keyword in this definition would be transferred from one object to another. Enthalpy means something else. So don't get confused. We don't use an H to represent heat, we use a Q. Since heat is just energy, its unit would be in joules. That should be obvious. The definition of thermal equilibrium is when two objects which are in contact with each other have a net transfer of kinetic energy, or a net transfer of heat, of 0. And in that situation, they're going to have the same temperature. So it's really important to remember things that are in thermal equilibrium have the same temperature. It's kind of easy to get confused. A heat engine is some device which is capable of taking some external source of heat and converting it to work. So this is where we're going to bring in what we learned last time. So example sources of heat are things like gasoline that you've lit on fire. That's what's going on inside your car engine. Steam, that would be going on inside like a big power plant, like a nuclear power plant. Or if you're feeling real evil, you could use liquid hot magma. Examples of doing work could include something as simple as spinning the blades on your lawnmower, or something a little bit more complicated like using a bunch of gears and stuff to transfer that energy into linear motion, kind of like what we learned about last year. And so we see these all the time. We use heat to make things move. Now we should be equipped with all the tools necessary to be able to describe that. Okay, so remember from last time that when a gas expands, they're capable of doing work. They exert a force, something moves, that means they've done work. And so we should be familiar with, rather, let's do this a little bit at a time, with a picture like this, where a cylinder of gas goes from a small volume to a large volume, and in the process, it does some amount of work. And so we did the derivation of how we got work equals negative P delta V last time. So that's how we can figure out work. Now, something expanding like that probably didn't happen on its own. What probably happened is that heat was added to it to give it more internal energy, which then allowed the gas to do work. So without that heat added, that process probably didn't happen. If it happened spontaneously, it's probably because heat was added later and we just prevented it from happening right away. So the next question is, how do we quantify that? And we're going to call this real important big idea the first law of thermodynamics. We're going to relate it to something we learned last year. Remember the work-energy theorem? Work equals change in energy. Energy is lost and something has done work on an object or a system. Well, we're kind of going to have the same thing here. The only difference is that now we have two ways to change the energy of a system. We could do it through mechanical work, like we just talked about a second ago, and we can also do it through heat. Now, it's important to realize we're dealing with systems. Remember, systems can only have kinetic energy, therefore they wouldn't have any potential energy in a system. So it's important, if just an object. And so it's important to remember that we're dealing with systems here. To kind of put that into an equation, we can say delta U, remember that is the internal energy of a system, is equal to work plus Q. This is the equation statement of the first law of thermodynamics. Basically what we did is we just rewrote the work-energy theorem, which we learned last year, in terms of a thermodynamic system where heat is possible to be transferred back and forth. Now be careful with the signs, it's easy to get confused. The big idea is that both work and heat are positive when they cause our gas to gain energy. So positive means that the gas has gained energy. That's our system. We understand that, then it should be easy to keep these signs straight. So work done is negative when the gas does work on its surrounding and expands, kind of like we talked about last week. Work is positive when the surroundings do work on the gas. That means delta V is negative and the gas is being compressed. Q, or heat, is positive when heat is added to the gas. It's like we take a flame and heat it up with a flame. Heat is negative when heat is removed from the gas. It's like we take the cylinder of gas or whatever and we rub it with ice cubes. Heat would be leaving the gas, warming up the ice cubes in that situation. So let's look at a simple example, and then we'll move into a more complicated example. Suppose that we have a cylinder of gas that's got a movable piston on it, and we add, with a flame, 1,000 joules of heat. The net effect is that the piston does 300 joules of work. The question is, how much energy did the gas absorb? So how much did its internal energy change by? So we kind of drew a picture. We started with something like this. We went to something like that. We added 1,000 joules of heat, so that's like a fire underneath it or whatever. And then the gas did 300 joules of work in expanding. And so the question is, how much leftover energy is there for the gas to absorb? Now the first thing we have to remember is that because the gas expanded, the work done is negative. It's losing energy as it pushes that piston up. Just like you lose energy when you lift something up on top of a shelf. Same idea. So the work done is negative because the gas is doing work, therefore losing energy. And so, first law of thermodynamics, delta U equals Q plus W. And so, simply adding those two together will give me something in the neighborhood of 700 joules. So basically we got 1,000 joules in, 300 out, the leftover is 700. So remember that the internal energy is proportional to the temperature. So we have the equation delta U equals 3/2 nR delta T. So we could use this information and the number of moles, if we knew it, to calculate the temperature change of the gas. So let's just suppose the gas started off at 300 Kelvin. A reasonable final temperature would be something like 350 Kelvin. It got warmer. So later on we'll do an example of actually using temperatures and putting more numbers into that. And later on is right now. So here's a real quick example. Not quick, a real simple example. Suppose we got 0.1 mole of an ideal gas that goes through the following process on a PV diagram. So it starts at 3 times 10 to the 5th pascals of pressure and then is dropped to 1 times 10 to the 5th pascals of pressure, while its volume changes from 0.5 times 10 to the negative 3 cubic meters to 1.5 times 10 to the negative 3 cubic meters. And our question is, how much heat was added to the gas? So we know the first law of thermodynamics, delta U equals Q plus W. So rearranging it, that would give me Q equals delta U minus W. Q is what we're looking for here. Well, we can't find the work using negative P delta V because pressure's changing. So this is where we have to use the area to find the work done. And so that shape's area will give us the work. I would divide that up into two simpler shapes, namely triangle and a rectangle. Because I know the area of a triangle and I know the area of a rectangle, then I can just add them together. So 1/2 base times height is the area of a triangle, base times height is the area of a rectangle. The base would be 1 times 10 to the negative 3rd. Height would be 2 times 10 to the 5th for the triangle. 1 times 10 to the negative 3rd is the base for the rectangle. 1 times 10 to the 5th is the height of the rectangle. And so all that's just some fancy geometry to show us that we got 200 joules of work in this gas expanding. Now we have to again realize it is expanding, therefore we need a negative sign in front of the work. Okay, that's step one. Step two, we need to figure out what the internal energy change is. Here's where we need to remember that the internal energy change is equal to 3/2 nR delta T. By the way, that's something important to remember. It's not something that's given to you on like the formula chart. Something you might want to put in your brain. Now we can find the temperatures from a PV diagram by using the ideal gas law. PV equals nRT, so T equals PV over nR. So crunching the numbers, I'm not going to show my work here because it's something we can do. Temperature at point 1 is 181 Kelvin, and the temperature at point 2 is 181. It should be joules, excuse me, it should be Kelvin, not joules. So it's the same temperature at both the first and the last points. That tells us that the net internal energy change is 0. Which means that the internal energy did not change during this process. So delta U in our equation is 0. So Q and W must be the same but with opposite signs. And so if the work done was negative 300 joules, then the heat added had to have been 300 joules. Now this is a rare and special example of a thermodynamic process. Next time we'll call it an isothermal process. But it kind of illustrates the problem-solving method here. The amount of energy that the gas gains has to be equal to the sum of the heat added plus the work. So, just to kind of get an idea of what the bigger picture looks like, let's draw a quick LOL chart for our gas. So there's the internal energy of the gas beforehand. We had 300 joules of heat added to the system. 300 joules of work was done on the surroundings. So the potential energy of the gas didn't change. So to kind of sum up, the big idea here is that work and heat can both change the internal energy of a gas. Energy's got to be conserved, so any work that's added or any heat that's added has to be lost or gained from somewhere else, and that's what that equation work plus Q equals delta U tells us. So there's a lot more to the picture here, but we'll wait until next class time to go into a little bit more detail. And then later on we'll learn about 4 special processes that we need to understand. So we've taken a big jump in our understanding of thermodynamics today. Please be sure to write down any questions you might have so that you can ask them at the beginning of class next time. Otherwise, be prepared to try to use this during class next time. Till then, ta-ta.